we're going to be drawing a lens and we're going to investigate refraction of a converging lens. Now, so this is a convex lens. If you have a ray that's going in this direction, so this is glass and this is air. Now, if you draw the normal, that's the normal to this surface, and it bends, is it towards the normal or away from the normal? So if it's going into denser material, it will go towards the normal. If you think about air and water, so this is still normal, and light hits there. However, it's refracting. So a denser material will go towards the normal. So if this is the normal to the surface, then rather than going straight through, so straight through would be here, it will go more towards down in this direction. And then we draw the normal to this surface, so this surface will be here, and it will bend towards the normal again. Is that correct? No, because this is glass and it's going into air, so it's going away from the normal. So normally it would go like this. However, because it's going more away from the normal, so rather than going upwards, it will go down. So it would have passed through a straight line, so it would have gone more down. Similarly, if we have a ray going this direction, we draw the normal to the surface, and normally it would have passed straight through if there was no material. However, it bends towards the normal because this is more dense, so it will go up, and because now this is going to less dense material, it's going away. So if this was going towards the normal, this is going away from the normal. Now the normal would look something like this. So it's at right angles to the surface, right angles to the surface. So that is the normal. Normally it would pass straight through, but it going away from the normal because less dense, and so it will be going in this way. All right, so now what happens when the lines meet? What is that term when the lines meet? So is it called the focal point? Is it called the focus? It's the focal point, or yes, so it is the focal point. All right, so let's just say that you have a source, and instead of having parallel rays, now you've got a source and it's emitting in all directions. So what happens now? All right, so let's draw the normal and see what happens. So this is the normal to this surface. It's going into denser material, so it's going towards the normal. So normally it would go straight through. If this is a straight line, it would have gone straight through. So it would have gone straight through, but because it's going more towards the normal, it would go Similarly here, the normal to this surface is like so. If there was no material, it would have gone straight through. However, it's going towards the normal, so it's going more like this. Actually, it's less. Okay, and then if you were to draw a normal to the surface, so that's the normal to that surface, and it would have gone sort of like this. However, because it's going to a less dense material, rather than going towards the normal, it would be away from the normal, so it would go more straight. Similarly here, the normal to this surface would be at right angles, so that would be at right angles like so. And again, it's going to less dense material, so it would have that looks quite close, doesn't it? That looks quite close. Okay, so it's going away from the normal, so it would go parallel. So can you see from the diagram, if you have light coming from this point in all directions, the outgoing ray would go parallel. So this is parallel, and this is from a focus, focal point, let's just say. So this is the focal point, and once it goes into a convex lens, it will come parallel. Now, a converging lens can form an image of an extended object. So let's see if we can find the position and magnification of an image that is made by a thin converging lens. Now, this line is the principal axis. So this is halfway symmetrical. So this is called the principal axis. And you draw lines parallel to the principal axis. Now, we met before, when you have parallel rays on the left-hand side and it's going from left to right, you'll meet a focal point. So let's get a ruler. And it also goes through the middle. Now, anything that goes through the middle will just go straight through the material as though it is a straight line. It's going to be very long. All right, so and if we extend this line over here, so here it meets there. So this was the image, let's just say. And this is, say, that's the focal point. All right, so let's label this diagram. So this is the object, this is the image, and the distance from there to there is the object distance. So let's just call this S1, and let's just call this, from the distance from the lens to the image is S2, let's just say. Actually, let's call that, okay, let's call that SO and SI. And where is the focal length? So the focal length will be from the lens to the focus, to the focal point. So this is F. Now the formula for this is 1 over S0 plus 1 over SI is equal to 1 over F. That is the formula for lens. Alright, so if we use this equation, let's just see what happens. Alright, so I'm going to use a ruler. Now let's measure the distance from the object to the lens. So this is about, well, let's do it from there to there. This is about 13.5 centimeters. So this is 13.5 centimeters. And we want to work out the distance from the lens to the image. Now the focus, the distance of the focus is about, well, let's just say it's about 9.5. So F is 9.5. And we want to work out SI. So 1 over SI is equal to 1 over F minus 1 over S0. So SI is equal to 1 over this. Is equal to 1 over F minus 1 over S0. Right, so if we plug in 1 over F, so 9.5 to the power of minus 1 minus 13.5 to the minus 1. So that is equal to that. And answer to the minus 1, you get 32. So it's roughly 32 centimeters. So we get SI is equal to 32. And that looks more like the length of a ruler. So the length of a ruler is, obviously this is not very to scale, so it is more than 30 centimeters. So it is quite close. So we did get 32 centimeters as the distance from the lens to the image. That should be centimeters. So that should be centimeters. Now, what about diverging lens? So we've discussed converging lens, and what about diverging lens? Now, suppose a beam of parallel rays are going into this lens, it diverges. So let's just have a look. Okay, so we've got an array of parallel rays. So now let's draw the normal to this surface. So the normal to this surface is 90 degrees. It's going into a denser material, so it would have gone straight through. However, it's going towards the normal, so it would go like so. Now let's draw the normal to this surface. So the normal to this surface would go like this. So that's the normal to that surface, 90 degrees to this surface. Now it's going into a less dense material, so instead of going towards the normal, it's going away. So let's draw what would have happened if there was no material. That would go straight, that would be straight. However, because it's going away from the normal, it will go more up. So it will go more up. Now, can you just see that this will go in the opposite direction because it's symmetrical? So just because of symmetry, it would go just because of symmetry. And if you were to draw it, you would get this. So I'm just doing a shortcut because of symmetry. I'm just drawing it like that. Symmetry about the x-axis. So this is a diverging lens. Now we will have a problem because the problem is what happens if the image is less than a focus. Okay, so what do we mean? So, well, let's just draw it. So if I have a convex lens rather than a diverging lens, and we have the image here, let's just say that this is the image, and it is less than a focus. So what I mean is that what if the focus was right here? So if the focal length was more than the object distance, that's what I mean. So I mean this is the object. So if the object distance is less than the focal length. So let's just see what happens. So that's the center, and you need a ruler for this. Paper, piece of paper. So that goes into the middle, and it goes through the focus. And then here, the goes through the middle of the lens. Now, can you see that these rays will diverge? They will never meet, meaning that you won't get the image. So this is the object. You won't get an image. However, you will get an image if you were to trace backwards up here. So what happens if you were to trace back the image? So let's draw a line, and you draw a line here. I do have a ruler. All right, so this will be the image. So this is the image. This is the object. So this is what happens if the object distance, so if the object distance is less than the focal length, where the focal length is from there to there. So now what is the image distance? So the image distance will be from there to there. Now let's see what happens if we put some numbers in. So if you remember, 1 over s object plus 1 over s image is equal to 1 over f. Now we want to work out the image distance. So if the object is, let's just say 6 centimeters. So this is this one. So 1 over 6 plus, and the focal length is 15. 1 over SI. So rearrange. We get 1 over SI is equal to 1 over 15. 1 over 15 minus 1 over 6. And so therefore SI is equal to 1 over all of that. So what do we have? What do we get? So let's put the numbers in. So you get 15 to the minus 1, 15 to the minus 1, minus 6 to the minus 1, and we inverse that. Oops, answer to the minus 1. You should get 10, minus 10. So it's minus 10. Let's see if that's minus 10. Well, we get 14. We get 14. Okay, so SI is equal to minus 10. This is calculated. Where have we gone wrong? That's 15. That's the focal length, and the object is 1/6. Image is 1/14. It's 1/4. It's 14. Well, the main thing is that it's negative. I know the drawing is not very accurate because the way I've drawn it, it's all very not straight. So here, because of the minus, what that means is that the image has gone in the opposite direction, and this will be a virtual image. So this is the calculated value. The measured value was 14 minus 14. If you look at this convex lens, a lens of this shape has an important property. When a beam of rays parallel to the x-axis and it passes through the lens, the rays will converge to a point that's called a focus and forms a real image at that point. And this image is real. So this is a real image. And such a lens is called a converging lens, or is called a convex lens. Similarly, if the rays passing through the focal point on the left and it emerges from the lens, it comes out as a beam or parallel rays. So if we look at diagram A and diagram B. So for A, if we have parallel rays coming into the convex lens, it will converge into a focal point. And if you look at diagram B, starting from the focal point, it will come out as parallel rays. Now, because you have a ray going straight through the center of the lens, now the center of the two surfaces are very parallel, and we assume that they're very close together. So there is refraction where the ray enters and leaves the material, but there's no net change in direction. So because you have that long parallel diagonal line going through the center of the lens, you can assume that it just goes straight through and there is no net change in direction.